Good morning, my dear students. Imagine you're at a bustling fair, standing near a drum. When the drummer hits it, you hear a deep boom almost instantly. But have you ever wondered why you can't hear the drum beating if you suddenly cover it with something like a vacuum jar? Surprising, isn't it? Today, we'll explore why sound needs a material medium to travel. Let's uncover what makes sound waves so special. Sound is what we call a mechanical wave, more precisely, a longitudinal wave. Think of it like a human chain passing a message by shaking their hands forward and backward. It travels by making the particles of the medium vibrate along the same direction the wave moves. This means sound particles do not travel themselves but pass on energy by vibration. Because of this, sound cannot travel through a vacuum where no particles exist to shake or vibrate. Why is that? In a vacuum, there are zero molecules or particles to pass on energy. So, when the source of sound tries to send vibrations, the waves have nowhere to go. This is why sound transmission in a vacuum is impossible. The energy can't transfer by molecular vibration. It needs air, water, or solids as the highway. When a vibrating object moves forward, it compresses the nearby air particles, producing a region of high pressure. This is called compression. As the object moves back, it creates a region of low pressure known as rarefaction, where particles are spread out and the local density decreases. These compressions and rarefactions travel through the air in the direction of the wave motion. They transport energy, but not matter. The longitudinal displacement of air molecules results in pressure variations, which can be modeled using the following equation: P of x, t equals P naught multiplied by sine of open bracket kx minus omega t close bracket, where k equals to pi by lambda. Here, P naught is the maximum pressure variation, k is the wave number, omega is the angular frequency, and lambda is the wavelength.
The speed of sound depends on the medium's elasticity and density. Materials that are more elastic and less dense allow sound to travel faster. In gases, the speed of sound increases with temperature because molecular motion becomes more energetic. The formula for the speed of sound in gases is V equals square root of gamma RT divided by m. Here, gamma is the adiabatic index, R is the universal gas constant, T is the absolute temperature, and m is the molar mass of the gas. Sound travels fastest in solids, then in liquids, and slowest in gases. This happens because the intermolecular forces are strongest in solids, allowing quicker energy transfer. Humidity and pressure also affect the properties of air. They change the effective density of the medium, which in turn alters the speed of sound.
We are given temperature T equals 300 Kelvin, gamma equals 1.4, R equals 8.314 joules per mole per Kelvin, and m equals 0.029 kilograms per mole. We need to find the speed of sound, V, in air. For ideal gases, the speed of sound is given by the formula V equals square root of gamma RT divided by m. Now substituting the values, V equals square root of open bracket 1.4 multiplied by 8.314 multiplied by 300 divided by 0.029 close bracket. This equals the square root of 120,414.5, which is approximately 347 meters per second. So, the speed of sound is about 347 meters per second, which closely matches the standard value under normal conditions. The general formula for the speed of sound is V equals square root of B divided by rho. Here, B is the bulk modulus of the medium and rho is the density. In gases, the speed of sound depends on temperature. That is, V equals square root of B divided by rho, which is also written as V equals square root of gamma RT divided by m. Compressions and rarefactions represent zones of pressure variation. These zones move parallel to the direction of wave motion. Finally, the speed of sound increases with elasticity and temperature. It is highest in solids, lower in liquids, and lowest in gases.